Next, we look at section 3.6 on prime factorization and greatest common factors. So we're looking at numbers in more detail, and how to break a number up into smaller factors. That's very important when you're working with fractions. So a number like 10, so the number 10 factors into a product of two smaller numbers. 10 is equal to 2 times 5. So 10 is called composite. But a number like 11, so 11 doesn't factor into smaller numbers. 11 is called prime. Okay, so every positive integer is either composite like 10 or prime like 11. Well, every positive integer except 1. So 1 is a special case. Not prime, not composite. But every number 2 or higher has to be prime or composite. So here, looking at the first few numbers. So 2 is prime, 3 is prime, 4 is composite. It breaks down as 2 times 2. 5 is prime, 6 is composite. You get the idea. So so 9 is an odd number that's not prime, so 9 is 3 times 3, so 9 is composite. Example 1, factor 150 into the smallest numbers possible. Okay, so we want to break up 150 as much as possible. So any number that ends in 0 has 10 as a factor. So 150 is equal to 10 times 15. But we can do better. So now we can break down 10. So 10 we saw already is 2 times 5. Also 15 is 3 times 5. So we can draw a diagram. So so first 150 breaks into these two pieces, and then these break into smaller pieces. Okay, so these are the we can't break down 2 anymore. These are all prime numbers, so they don't break into smaller pieces. I mean, you could write 2 as 1 times 2, but apart from 1, it doesn't have any smaller factors. Okay, so these numbers on the bottom are the small factors we're looking for. So 150, it's 2 times 5 times 3 times 5. We can change the order. So usually put the smallest numbers first. So 2 times 3 times 5 times 5. Those are the smallest factors possible. 5 times 5, that's 5 squared. It's so nice to write it like this, but this is fine, and this is useful as well. Okay, so we found the prime factorization of 150. Okay, so every number, if you keep breaking it into smaller and smaller pieces, you'll eventually get to prime numbers. Okay, so the prime factorization of 150. So writing 150 as a product of prime numbers, it looks like this. And yeah, this is a good way to do it. So this factor tree, so yeah, it looks a little bit like an upside down, tree. Like this. All right, so any number you can break it down like this. It's just the numbers at the bottom we're interested in. So yeah, so we're not including 10 here. It's just the numbers at the bottom. Okay, another example. Is 31 a prime number? Okay, so maybe you know that it's prime already, but so how would you check? Well, let's see if it has any factors. So remember, a number is prime if it doesn't factor into smaller numbers. So you could start checking. So is 2 a factor? Is 3 a factor? How about 5, 7, 11? So so that's a good way to check if a number is prime. Just see if it has any prime factors. Okay, so for example, start with the smallest prime number, 2. So is 2 a factor of 31? So what happens if you divide 31 by 2? Okay, so this is going back to our division. So 2 goes into 31 15 times, remainder 1. Okay, so 2 is not a factor of 31. It doesn't divide in evenly. There's a remainder. Okay, so 2 is not a factor. Okay, and that was clear already. So 31 is definitely an odd number. How about 3? So is 3 a factor? Well, if you divide 31 by 3, it goes in 10 times, and the remainder is 1. And so again, it doesn't divide in evenly, so 3 is not a factor. Also, 5 is not a factor. It goes in 6 times, remainder 1. All right, yes, it's just a coincidence we're getting 1s, but the point is we are getting non-zero remainders. So 2, 3, and 5 are not factors. Well, the next prime number is 7, but we can already rule out 7 and higher primes because 7 squared is bigger than 31. So if 7 was a factor of 31, then it would have to be multiplied by a smaller prime, a prime smaller than 7. All right, so if the prime number is squared is bigger than the number you're looking at, there's no need to check it. Okay, so since 2, 3, and 5 are not factors of 31, then that's telling us 31 has to be a prime number itself, so it has no smaller factors. Okay, so 31 is prime. It's a useful fact. Example 3, use a factor tree to find the prime factorization of this number, yes, so 186. That's a kind of a big number. Let's see what we can do. Well, yeah, so right away, 186, it's certainly even, so 2 is a factor. So if you divide 186 by 2, you get 93. Okay, so this is the top of our tree. Yeah, so 2, that's a prime piece, but maybe we can factor this some more. Yeah, 2 is not a factor, but if you try 3, yeah, 3 is a factor. And so this is equal to 3 times 31. And that's the end of the tree. So yeah, 3 is prime, and yeah, 31 is prime. So this is the best we can do. We can't get any more smaller factors. So here's the prime factorization of 186. It's 2 times 3 times 31. All right, and yeah, so you could play this game with any number. So if you start with any positive integer bigger than 2, 2 or bigger, then it's going to have a prime factorization like this. You could ask, are there different ways to write a number as a product of primes? So that's what we're getting at in example 4. And so here we're working with the number 24. Draw 2 different factor trees for 24. And the question is, do you get different prime factorizations? Okay, so starting with 24, you could make this factor tree. So 4 times 6 is 24. And then 4 breaks down 2 times 2, 6 is 2 times 3. And then that's the best you can do. So circle these numbers at the bottom. 24 is 2 times 2 times 2 times 3. All right, there's another way to break 24. You could write it as 3 times 8. 3 is prime, but 8 is 2 times 4, and 4 is 2 times 2. Okay, so then these numbers at the bottom, you can see they're the same as these guys, just in a different order. But if you write it smallest to largest, then we're getting the same prime factorization. 24 is 2 times 2 times 2 times 3, or 2 cubed times 3. And in fact, yeah, so these prime factorizations are unique. If you order from smallest to largest, there's only one. Every number just has one prime factorization. So it doesn't matter how you do the tree, you'll always get the same answer. Okay, so here's the next idea we need, the greatest common factor of 2 numbers, or maybe more than 2 numbers. Okay, so it's GCF. And yeah, it's a good name. It's describing what it is. So if you have 2 numbers, you can look at all the factors of the 2 numbers, and then look at the factors that they have in common and pick the largest or the greatest. So that's what we're trying to find. Example 5, find the greatest common factor of these two numbers, 6 and 8. So we can make a list all the factors of 6. Okay, so what are all the numbers that divide evenly into 6? Well, 1 is a factor, it goes in 6 times. 2 is a factor, it goes in 3 times. 3 is a factor, goes in twice. And 6 is a factor, goes in once. Okay, so yeah, we're doing something slightly different here. So the prime factorization is, writing a number as a product of primes. Making a list of factors is different. It's finding all the factors of a number. Okay, the factors of 8 are all these guys, 1, 2, 4, and 8. Yeah, so for example, 3 is not a factor of 8. If you divide 8 by 3, the answer is 2, remainder 2, so 3 does not fit into 8 evenly, so 3 is not a factor. But these guys do divide in evenly. Okay, so we can see the common factors. They both have factors 1, they both have factors 2. Nothing else in common. Okay, so 1 is a common factor, 2 is a common factor. What's the greatest common factor? Well, the biggest number that's a factor of both is 2. Alright, so that's a nice simple way to find greatest common factors. Just list all the factors, look for the common factors and find the greatest. So the greatest common factor of 6 and 8 is 2. Example 6, find the GCF, find the greatest common factor of 7 and 10. So we can do it the same way. Yes, 7's a prime number, so its only factors are itself and 1. There are no smaller numbers that multiply to give 7. Okay, so all the factors of 7, just 2 of them, 1 and 7. 10 is composite. It has factors 1, 2, 5, and 10. Okay, so comparing these two lists, what's the greatest common factor? Just 1. Okay, so the greatest common factor of 7 and 10 is 1. Yeah, that's really telling us they have no factors in common. So that can happen. Example 7, find the GCF of 24 and 60. Okay, we can do it the same way, but now we're seeing a problem. Yeah, these numbers have lots of factors. So if you list all the factors of 24, it has all these factors. 60 has even more factors. Okay, so we see, they have common factor 2, 1, 3, 4, 6. And the greatest common factor is 12. Yeah, nothing up here is matched over here. Okay, so the greatest common factor is 12. But yeah, so this is what goes wrong if you're dealing with bigger numbers. Then this is a lot of work. Is there an easier way to work out the greatest common factor, especially when you're looking at big numbers? Yes. So the better solution is to use prime factorizations. All right, so 24. We saw this already. So 24 is 2 times 2 times 2 times 3. It's prime factorization. We saw this already, right? Yeah, there it is. 2 times 2 times 2 times 3. 60. Okay, we can make a factor tree. So 60 is, you could start 2 times 30, but it's, if the two numbers are roughly the same size, that's better. So 4 times 15 I like better. 4 is 2 times 2, 15 is 3 times 5. Alright, so the prime factorization of 60 is 2 times 2 times 3 times 5. Okay, so why is that helpful when you're looking for the GCF? Well, now you can just look to see what they have in common. So they both have 2's. In fact, they both have 2 2's. Okay, 24 has a third 2, but there's no matching 2 here. And what else do they have in common? Yeah, 3's. A 60 has a 5, but there's no matching 5 over here. So we're just looking what are the most primes they have in common. So it's just 2, 2, and 3. 2, 2, and 3. Okay, and that 2 times 2 times 3, that gives us 12. Okay, so that's the same answer, but this is especially for big numbers, this is a better way to find the greatest common factor. Okay, so we can see 24 is equal to 12 times 2. 60 is equal to 12 times 5. So yes, a 12 is the common piece. That's the greatest common factor. Yeah, and you can see there are other common factors, smaller common factors. So there's 2 times 3, 2 times 3, or 2 times 2, 2 times 2. Okay, so why do we care about the greatest common factor? Well, we'll see in a minute. Well, we'll see right now. Use the greatest common factor to reduce fractions to lowest terms in one step. Okay, so if we take these two numbers, 24 and 60, and make the fraction, say, 24 over 60. Well, suppose the question was to reduce this to lowest terms and simplify this fraction as much as possible, then we can use the greatest common factor at the top and the bottom. We can cancel that greatest common factor, so divide the top by 12, we get 2. Divide the bottom by 12, we get 5. So here's the equivalent fraction reduced. Okay, if you use the greatest common factor, then you reduce it to lowest terms. You can't cancel anything else. Yeah, if you just used a common factor like 4, so if you divide top and bottom by 4, here you get 6 over 15. But then you could cancel another 3. Okay, so you could do this in 2 steps, but if you want to do it in just 1 step, use the greatest common factor. Okay, an example of that. Find the greatest common factor of 54 and 99 and use it to simplify 54 99ths. Okay, so let's do it using our prime factorization method. Okay, so 54. Yeah, it's composite. It's 6 times 9, and then 6 is 2 times 3. 9 is 3 times 3. All right, so we've got it down to the prime level. So 54 is its prime factorization is 2 times 3 times 3 times 3. How about 99? Yeah, it's divisible by 9, so 9 goes into 99 11 times. 11 is prime, but 9 is composite. It's 3 times 3. So the prime factorization of 99 is 3 times 3 times 11. What are the primes they have in common? Well, 3 is a common factor, and they also share another 3. 54 has a 2, but there's no 2 here. 54 has another 3, but there's nothing to match it here. And 99 has an 11, but there are no 11s up here. So the greatest common factor is 3 times 3, or 9. Okay, so we can cancel 9s out of this fraction. Okay, so 54 divided by 9. Okay, so if you divide 54 by 9, you're left with 2 times 3, that's 6. And divide 99 by 9, you're left with 11. Alright, so here is 54 99ths reduced to lowest terms. Looks like this 6 11ths. Alright, so it's maybe a little complicated, yeah, especially if you're maybe seeing these factor trees for the first time. Okay, you could always do it the other way, so list all the factors of 54. Yeah, 54 is going to have a lot of factors though. Yeah, so I recommend, do it this way, especially for bigger numbers. So write out their prime factorizations and then look to see what they have in common. Yeah, we haven't looked in the book yet, so yeah, we're in this section. Okay, primes, here are the composite numbers. And yeah, just getting used to factoring numbers. Yeah, here's another way to find the prime factorization of a number. Just start with the smallest prime, 2. So keep dividing by 2 until you get a number that's not divisible by 2. then divide by the next prime, 3. Keep dividing by 3s, then 5s. So you can do it that way too, but yeah, I prefer the factor trees. In fact, yeah, the factor trees are more efficient. Yeah, so this is yeah, looking at some more complicated examples here. So if you're asked to find the greatest common factor of these two numbers, so they've already been put into, already found their prime factorizations, then yeah, it's again just looking to see what they have in common. So for these two numbers, first look at the 2's. So there's a single 2 here. Here we have 2 times 2 times 2 times 2, but to see what they have in common, they just have just one 2 in common. Let's look at the 3's next. So yeah, this is 3 times 3. Here we have 4 3's multiplied together. So 2 of those 3's match. So 3 times 3. And yeah, we have a 7. There are no 7's over here, and no 11's over here, so nothing else matches. All right, so the greatest common factor for these two, it's 2 times 3 times 3. That's 18. And yeah, another way to see that is, yeah, you're looking for the common primes and find the smallest exponent that appears. So for example here, yeah, so we've got a 3 squared. Here we have a 3 to the 4. So the smallest exponent is 2, and that's the one we need. It's just seeing what they have in common. Here the questions: find the greatest common factor of 3 numbers. Okay, so what's the biggest common factor, the biggest factor common to all 3? So if you look at the prime factorization of 60, it's 2 times 2 times 3 times 5. The second number, 135, breaks up like this. And 150 is, we saw that one already. Looks like this. So now we want to see what's common to all 3. Yeah, this middle one has no 2's, so 2 is not a common factor. They do have 3's in common. So this 3, one of these 3's, and this 3, this is common to all 3. 135 has more 3's, but it only matches with 1 3 in these two numbers. And they also have a 5 in common. All right, so the greatest common factor for these 3 numbers is 15. And yeah, so again, once you've, if you're trying to reduce a fraction to lowest terms, then work out the greatest common factor. Here it's 30, and divide the top by 30, divide the bottom by 30 to get it into lowest terms. All right, yeah, so here's a nasty looking example, but it reduces to 2/3 once you cancel the common factors. Yeah, so this 2 2's in common, 1 3 and 1 7. So this simplifies a lot to just 2/3. All right, so that's our main use for greatest common factors. It's for simplifying fractions. Okay, so there's a short section here on precancelling. In section 3.7. So what is precancelling? Yeah, it's when you're multiplying fractions, it's a nice shortcut. So it can make your life easier. So let's see, yes, example 9, multiply 5/6 by 9/10 and simplify your answer. All right, so let's do it the kind of a long way first. Okay, so 5/6 times 9/10. So you remember from last time, when you're multiplying fractions, you multiply straight across. 5 times 9 is 45. 6 times 10 is 60. All right, so we get the answer 45 over 60. Okay, you definitely get partial credit, but the question says to simplify your answer, so we want to reduce this. And yeah, you can see, yeah, any number that ends in 5 or 0 has to have 5 as a factor. So we can reduce this by canceling 5's. So 45 divided by 5 is 9. 60 divided by 5 is 12. Okay, is this the answer? Not quite. We can reduce it some more, so they still have a 3 in common. So 9 divided by 3 is 3. 12 divided by 3 is 4. Okay, now it's in lowest terms. 4 breaks down as 2 times 2, but there are no 2's in the top. So this is the answer, 3/4. Yeah, we could have, so we simplified this in 2 steps, but yeah, we could have used 1 step. So the greatest common factor of 45 and 60 is 15. That's the biggest factor they have in common. So yeah, so in 1 step, 45 divided by 15 is 3, and 60 divided by 15 is 4. All right, so yeah, so either way, this is it's actually more work than we need to be doing. So let's see the easier way. So the idea is to look for cancellation before multiplying. Okay, so that's why it's called precancelling. Your pre means before, so you're canceling before multiplying. Yeah, here we multiplied first and then did canceling. Okay, so why is this better? Well, okay, here's the problem again. So 5/6 times 9/10. Okay, so we have on top, multiplying straight across again, it's 5 times 9. On the bottom, 6 times 10. All right, so instead of getting 45 here, let's break down, let's factor these numbers and look for cancellation. Okay, so yeah, so on the top here I see 9 is 3 times 3, and 6 contains a 3, so 6 is 2 times 3. 10 is 2 times 5, and this 5 matches this 5. Okay, so remember for canceling, this is our idea. So if you have a number multiplying everything on top and the same number multiplying everything on the bottom, then you can cancel that number. All right, so here we have a 5 multiplying everything on top and a 5 multiplying everything on the bottom, so those cancel. And also we have a matching 3. Okay, so we haven't done any multiplying yet. First we did all the canceling we could. I mean, yeah, can I cancel these two 2's? No, because they're both on the bottom. It's always something on the top with something on the bottom. Okay, so we're left with just 3 over 2 times 2. Okay, now I'm going to finally do the multiplication. 2 times 2 is 4. Okay, so we get the same answer, but okay, as long as you're good at factoring, it's a lot less work. Okay, so no big numbers like 45 or 60. We didn't have to find any common factors. Okay, so this idea of canceling before you multiply, this is the precancelling. Okay, another example. Example 10, compute 12 times 5/8 times 2/3. And you remember that trick from last time, so to convert 12 into a fraction, it's just write 12 over 1. Okay, again, we're going to use precancelling, so we're going to factor these numbers and look for matching numbers on the top and the bottom. Okay, we're looking for numbers to cancel. Okay, so that 12 turned into 12 over 1. Okay, so yeah, I see a 3 on the bottom, and yeah, I know 12 is 3 times 4. So right away those 3's are going to get canceled. I see a 2 on the top. On the bottom, 8 is 2 times 4. Or 4 times 2. Yeah, we also have a 5 on the top, but that's not going to match. There are no 5's on the bottom, so the 5 doesn't cancel, but everything else does. And so I can cancel these 2's, these 3's. Okay, I mean, yeah, maybe you're worried these 3's are in different fractions, but you remember when you multiply fractions, it's all the tops get multiplied together, all the bottoms get multiplied together. So really, we're putting all these together. We just need a number on the top to match a number on the bottom. Okay, so everything canceled. We're just left with a 5 on the top and a 1 on the bottom. And 5 over 1, that's 5. Okay, so the answer is 5. And in fact, we didn't do any multiplying. Okay, we just did canceling. So yeah, if you did multiply, so doing this the long way, you get 120 over 24, and then you'd have to divide 24 into 120. It goes in 5 times. So you get the same answer, but this is a nicer way to do it, pre-cancelling. Okay, and the same thing here. So example 98, multiply these 3. So yeah, we can see there's a this 3 matches a 3 out of the 9, so we can cancel 3's. We can also cancel 4's here out of the 8 and the 4, and 5's out of the 10 and the 5. So we're left with just 2 times 2 and 1 times 3. So 4/3, yeah, that's an improper fraction. You can convert that to a mixed number, 1 1/3. Okay, yeah, we'll get into more mixed numbers later. Okay, so that's pre-cancelling.